Okay, so here let's take a look at a sample problem about the Coulomb's law. So it says figure A here shows two positively charged particles fixed in place on an x-axis. The charge are Q1 and Q2. So here you can see Q1 and Q2. And the particle separation is R, capital R equals 0.02 meter. So this is capital R, this is capital R. And what are the magnitude and the direction of the electrostatic force on particle 1 from particle 2? Okay, so this one will be easy. So we actually need to plug in the values into the Coulomb's law. So we have F12 equals 1/4 pi epsilon naught times the absolute value of Q1 and then times the absolute value of Q2 and over R squared. Okay, so actually here we only calculate the scalar and actually we only calculate the magnitude of the force. So we can just take absolute value of charge. We don't really need to care about the polarity of the charge, whether it is positive or negative. Then we just plug in this one and then we calculate a positive number and then we try to determine the direction of the force by another way. So so just put it like this, and then 1/4 pi epsilon naught is K, so which is a 0.99 times 10 to the 9th power. So in the middle, I don't expect you to write all the SI unit, but for the answer, you need to put the full SI unit for the variable. Okay, so here we have this is K and then times Q1 is 1.6 times 10 to the minus 19, and then here 3.2 times 10 to minus 19. Okay, so this is Q1 and Q2, or absolute value of Q1, Q2. Okay, actually Q1, Q2 are all positive. Okay, and R, maybe we can just write it as a capital R squared. So yeah, so this is 0.02 and then quantity squared. Okay, so using a calculator, we can know this value will be 1.15 times 10 to minus 24 Newton. Okay, so actually, when we consider F12, which means the force acting on charge 1 from the charge 2. So F12 in the vector form is, okay, so we expect this one is the x-axis, the right side is the positive x-axis. So it will be negative 1.15 times 10 to minus 24 Newton, and then times the unit vector of x-axis, I hat. We call it I hat. Okay, so this is the first answer. Okay, so I would like to let you know is ijk, I hat, j hat, and k hat. We denote these three vector to be the unit vector in Cartesian coordinate. 直角坐标系 coordinate. So this is in x-axis, in y-axis, and in z-axis. Some textbook, they may write it as a x hat, y hat, or z hat. Or maybe some other will write it as a ER, EX, EY, EZ, so on and so forth. But generally in this textbook, I will use this kind of notation, I hat, J hat, K hat for X, Y, Z axis. Okay, so, and of course, actually they are univector, which means that the magnitude of them will be 1. Okay, will be 1. Sometimes I will just write it like this. They just skip the dot, and also J will be like this. Yeah. Yeah. So they are actually the same. Okay, so next, this is for part B. And here it says figure C is identical to the previous one, except that particle 3 now lies on the x-axis between particle 1 and particle 2. So just now we have Q1 and Q2 separate by R, still separate by capital R. And then here we place particle 3 in between, and then Q1, Q3, and of course they are in the same axis. And then the distance from Q1 to Q3 is 3/4 of R, 3/4 of R. And then Q3 has a charge negative 3.2 times 10 to minus 19 and blah, blah, blah. So what is the net electrostatic force on particle 1 due to particle 2 and particle 3? Okay, so here we have 3 charges, and then we would like to know the forces acting on Q1 from Q2 and Q3. So now we already know F12, the force acting on Q1 from Q2. So the next step is to calculate the force acting on Q1 from Q3, and then we add these 2 vectors together. Okay, so F12 will be the same because the distance and the charge amount are also the same. So F12 is actually the same. And here we calculate F13. So actually we can write it as 1/4πε0, but we can also simply write it as K. So it is K times absolute value of Q1 times the absolute value of Q3 all over. So the distance is not capital R anymore. The distance should be 3/4 or 3/4 of R, and then quantity squared. Okay, so we can just plug in the number. K is 8.99 times 10 to the 9th power, and then times Q1. Q1 is this one, 1.6 times 10 to minus 19, and then times Q3. The absolute value of Q3 is 3.2 times 10 to minus 19, and then all over. This is 3/4 square is 9/16, and then times R square. R is still 0.02, and then square. Okay, so this number will be nothing but 2.05 times 10 to minus 24 Newton. Okay, so and actually this is a negative charge, this is a positive charge, so they attract each other, and F13 will point to the right side. So in this sense, F13 will be 2.05 times 10 to minus 24 Newton, and then in positive x-axis, which is I hat. Okay, so this is F13. So the total F acting on F1 will be F1 common net will be negative 1.15 times 10 to minus 24, and then plus 2.05 times 10 to minus 24, and then all multiplied by I hat. Okay, so the answer will be 9 times 10 to minus 25, because part of the force are cancelled. So this is 9 times 10 to the minus 25 Newton, and then I hat. Okay, so this is the net force acting on particle 1. Okay, so and next, part C. So it says figure E is identical to the previous one, except particle 4 is now included and has charge Q4. So we still have Q1, Q2 separated by capital R. And then here, rather than placing the Q3 on the x-axis here, we only place the Q4 with an angle theta to x-axis. And then the distance is still 3/4 of R. So it lies on a line that makes an angle theta equals 60 degrees with the x-axis. So what is the net electrostatic force on particle 1 due to particle 2 and 4? So still, the setting of a Q1, Q2 are the same. So F1, 2 are still these values. Okay, so next we would like to calculate F1, 4. So it is K times absolute value of Q1 times absolute value of Q4 all over the distance, 3/4 of R and then quantity square. So we can just plug in the number. This is 8.99 times 10 to the 9th power, and then times 1.6 times 10 to minus 19, and then times 3.2 times 10 to minus 19, and then over 3/4 times 0.02, and then quantity square. So actually the values should be actually the same. The magnitude of the force, F1 force, should be actually the same as F13, which is 2.05 times 10 to minus 24 Newton. Okay, so actually the force F1 force should point to the top right, like this one. And actually we now need to add F14 and F12 and F14 together. And of course, they're not pointing to the same direction or opposite direction, which means that we need to decompose it, F14 into x-axis component and also y-axis component. Okay, so in this sense, F14 vector should be 2.05 times 10 to minus 24, and then times. So this theta is 60 degree, is 60 degree. So the x-axis component should be this side over this side will be cosine. So we multiply by cosine of 60 degree. And then here we have a Newton and then I hat. Okay, so this is the x-axis component. And then plus the y-axis component will be 2.05 times 10 to minus 24, and then times sine of 60 degree, and then Newton times j hat. J hat will be the y-axis, the unit vector in y-axis. Okay, so this is F14. Okay, so now we can just add F12 and F14 together to form F1 net. Okay, so will be F12 plus F14. Okay, so and this number will be negative 1.25 times 10 to minus 25 Newton I hat, and then plus 1.78 times 10 to minus 24 Newton j hat. Okay, so this is the force. This is the total force acting on particle 1. So it will be like something like this. This is F1 net. Okay, so far any questions? So far any questions? Okay, if no question, we can move on. Okay, no question. Okay, we can move on. Okay, so next we have another sample problem. Um, so it says, uh, figure A shows two particles fixed in a place. Um, so a particle of charge Q1 at the origin, Q1 at the origin is positive AQ. And of course, we don't know what is the value of Q, but it doesn't really matter in this question. Okay, so and the particle charge Q2 is negative 2Q at x equals L. So this is Q1, this is Q2, and then they are separated by capital L. Okay, at what point other than infinitely far away can a proton means a particle with positive charge of 1.6 times 10 to minus 13 Coulomb. Okay. So and can be placed so that it is in equilibrium. Equilibrium means there is no force acting on it to accelerate it, because due to the Newton's second law of motion, Newton's second law of motion, F equals ma. So if there are any force acting on an object, then there will be an acceleration, and then the ratio will be the mass of this object. So if it's in this problem that it is in equilibrium state, which means that there is no force acting on it. So the net force on it is zero. So it is equilibrium point stable or unstable. So this concept might be a bit out of the topic of this course. So if you can accept this, then it will be fine. Maybe later on you will learn some theory about the control theory, which will discuss the stability of a system in a deeper way. But here, we just try to understand the concept of stability in a very simple way. Okay, so let's move on. So just now it says we try to put a proton in between so that there is no force acting on it. So, and of course, try to put it on the x-axis, because if we try to put it out of the x-axis, maybe somewhere here, then you can simply imagine that this force may be in this axis, either attracting or repelling, and so as this one. And on the y-axis, it can never be cancelled to be zero. Can never be cancelled to be zero. For example, if the force is something like this, then these two forces pointing to a different direction, they can never cancel the y-axis component. So so we can quickly know that this proton should be placed on the x-axis. So there will be three cases: in the left part, in the middle part, or in the right part. Okay, so the first case is if we put the proton between Q1 and Q2, what would be the results? So first, Q1 and the proton are all positive charge, so they will repel each other, which means the force acting on the proton will be pointing to the right side. So the first one is this one. Okay, so and we consider the proton and the Q2. This is positive, this is negative. So these two charges will attract each other, which means that the force acting on this proton will also point to the right side, like this. So the only two forces acting on the proton are all pointing to the right side, so they can't cancel each other, because we hope the force acting on the proton to be zero. We hope these two forces cancel each other perfectly. Then there will be no force acting on this proton. But this is not the case, so we try to reject this case, reject it. Okay, so and the second case is if we put the proton on the left side, So this is the proton, and Q1 and Q2 will attract each other, so that the force will point to the, sorry, will repel each other. This is positive, this is negative. So they repel each other. They repel each other. And for this proton and the negative charge, they're in opposite polarity, so they attract each other, which means F2 point to the right side. So it might be okay, but when we try to consider in a deeper way, then we can also reject this case. It is as follows, because Q1 has positive AQ. This is positive HQ. And then Q2 is negative 2Q, negative 2Q. So when we try to consider the magnitude of F1, the force should be proportional to Q1 and the QP, and also over R squared. So this is, maybe we call it R1. This is R1. This is R1. So this is F1. Okay, we call it proportional. So we just ignore the K or 1 over 4 pi epsilon naught. And then also F2 proportional to Q2 QP and then R2 square. Okay, so they are both proportional to QP. So the QP doesn't really matter. And then we can see that maybe we can just take the absolute value. This is AQ, which means that Q1 is larger than Q2. And then also R1 is this distance. And then R2 is this distance, which means Q1, the absolute value of Q1 is larger than absolute value of Q2, and then R1 is a distance, so it must be positive. So R1 is less than R2. So when we try to plug in these two values into here, and then these two value into here, we can clearly see that F1 should always be larger than F2 when we try to put the charge on the left side. So we also reject this. These cases. This case. Okay, so for the third case, we put the positive charge on the right side. So in this case, Q1 is larger than Q2. Absolute value of Q1 is larger than the absolute value of Q2. And here, this is R1, this is R2. So in this case, R1 is also larger than R2. So there may be a point to make it like Q1 over R1 square equals Q2 over R2 square. So there may be a point satisfy this condition. And then it will make F1 and F2 perfectly cancel each other. So we would only need to consider this case. So here, let's try to calculate what should be the point. Okay, so here we have F1 equals F2. Consider the magnitude. So here let's consider this is L. This is capital L, the distance between Q1 and Q2. And then we call the x-axis coordinate of the proton called small x. Okay, so F1 will be like K times Q1 and then QP all over x squared. Okay, and then F2 will be K times, maybe we just put the absolute value here, absolute value of Q2 times QP, and then all over. So this distance should be x minus L, So x minus L and then quantity squared. So here we can simply cancel K, cancel QP, and then we can also plug in Q1 will be 8Q, and then over X squared equals the absolute value of negative 2Q is 2Q, and then X minus L quantity squared. Then we can also cancel Q, and then here we have a 4, this is 1. Okay, so we can do some simple algebraic calculation. Then we will get, okay, so this is 4 times X squared minus 8XL plus 4L squared equals X squared. Okay, so we just move over this one. We have a 3X squared minus 8XL plus 4L squared equals 0. Okay, so we can do some factorization. We can know the answer should be X equals 2/3 of L or 2L. Okay, so we have 2 solutions for this quadratic equation. But suppose we already assume that the proton is on the right side, which means that this X should be larger than L, so that it should be on the right side, which means that we would try to discard this solution, discard this one. So the only solution will be X equals 2L. So X equals 2L will be the solution. Okay, so furthermore, it asks you whether this equilibrium is stable or unstable. So it is a bit difficult to explain. So let me try to tell you the answer is this equilibrium point is unstable. It's unstable. It means if we try, yeah, so actually, maybe let me try to add a page. Okay, so just now we have Q1, and then Q2. This is also, this is negative, right? Yeah, this is negative. And then we know this proton should place here. This is the proton. Okay, so this is L, this is also L, so that it adds up to be 2L. Okay, so whether it is stable means if we try to put it perfectly at X equals 2L, then there will be no force acting on this proton, so no problem. But if we try to move it slightly to the right or slightly to the left, then whether it will go back, it is just like if we have a curvature like this, and then of course, if we place a ball, here, then of course it will just roll down and then roll up, and then of course there are some friction force, so that it will going back and forth, and then until they end up to be stay here. So this is called the stable equilibrium point, which means that even if you try to push it to the left side, it will try to roll back. But another possibility is like this is a curvature, and then if you try to put a ball here, suppose there are no force acting on it, then this ball may just stop there perfectly. But if you try to push it slightly to the right side, then this ball will just fall over. Or if you try to push it to the left side, then it also will fall down. So this is sort of unstable. So let us try to consider whether it is stable or unstable in a mathematical way. So if we try to write F net will be K times, this is AQ, and then times QP all over X squared, and then minus 1 over K, and then times, should be K, and then times 2Q, and then QP over x minus L squared. Force should be like this, And then we can try to do some simplification, will be like 2k qp, and then times 4 over x squared minus it should be 1 over x minus L quantity squared, like this. Okay, so if x is perfectly 2L, then f net should be perfectly 0. So here, if we try to put x to be 2L plus a small distance, delta L. Okay, we try to put it there. Of course, this is a positive multiplier, so we don't care about that. We only care about this. We only care about this factor. So if we try to put x to be 2L plus delta L, it will be like 4 and then 2L plus delta L quantity squared minus 1 over 2L plus delta L minus L and then quantity squared. So this L cancel with this 2, and then and then we can have we try to factor it out. So it is 4 over 4L squared plus 4L delta L plus delta L quantity squared minus 1 over L squared plus 2 delta 2L delta L plus delta L quantity squared. Okay, so we try to do a bit more. So it is 1 over L squared plus L times delta L, and then plus delta L quantity squared over 4 minus, this should be L squared plus 2L delta L plus delta L squared. Okay, so here we assume delta L is much smaller than capital L, which means that we can ignore this square term. You can simply imagine if L is 1 meter, this is 1 millimeter, then if we take square, then this term will be very, very small, much smaller than this term. So we can ignore the final term. Then we can easily check that this one is smaller than this one, which means that this one should be larger than this one, which makes this factor to be positive, which means that if we try to put x to be slightly larger than 2L, there will be a force, positive force acting on it, which means that if this one move to 2L plus delta L, there will be a force acting on it. This one is a positive force. Oh, yeah, this is a positive force to push it away, which means that it is unstable. So if you can get it, then it will be fine. It may be helpful to you later on, but for this seminar, if you can really accept the concept of stability, then it will be fine. It just occur once here. It will not occur again. So far, any questions? Okay, so let's move on. Okay, so here just come a few a few concepts. So it is called charges quantized. So it says electric charge is quantized with respect to certain values. So the charge of a particle can be written as n times E. So where n is the positive or negative integer, negative or negative integer, which means integer. Okay. And it's a positive or negative integer. And E is the elementary charge. Okay, so we have E is the elementary charge. It will appear force again and again. So E is 1.602 times 10 to minus 19 Coulomb, but usually we will just write it as 1.6 times 10 to minus 19 Coulomb is sufficient. We don't really need to care about the 0.002 to the 10 to the minus 19 Coulomb. Okay. So 1.6 times 10 to minus 19 is enough. Okay, so it means that this n should be an integer, and of course you can also consider 0 as the one of the possible n. Yeah, if n is 0, which means there is no charge, it is perfectly neutral. So yeah. So here we have a Q equals NE. Q equals NE. The total charge amount should be a multiple of the elementary charge. Okay, so it also mentioned that electron. So in the chemistry class, you know electron, proton, and neutron. So for the electron, it has a 1 unit of elementary charge of a negative sign, and then for the proton, it has a positive E. It has a positive E, and for the neutron, it is electrically neutral. Okay, so so it says when a physical quantity such as a charge can only have discrete value rather than any value. So we say that the quantity is quantized, 量化或者 in physics is called 量子化. Okay, so it is possible, for example, to find a particle that has no charge at all, or charge of 10e or negative 6e, but not a particle with a charge of say 3.57e. So it must be a integer multiple of the elementary charge. Okay. So here comes a quick checkpoint. So it says initially sphere A has a charge of negative 50e, and sphere B has a charge of a positive 20e. So let's draw it out. We have a sphere A, and then we have another sphere B. So this is A with a negative 50e. This is a plus 20e. Okay, the sphere are made of conducting material and are identical in size. So identical in size. So if the sphere then touch, what is the resulting charge on sphere A? Okay, so the condition identical in size is important because it means that after these two spheres touch each other, then the charge will be shared by them equally shared by these two spheres. So this condition will give this condition. Okay, so who knows the answer of this checkpoint? Who knows the answer of this checkpoint? So if you know, you can try to type it on the chat room, and then I'll mark it down to add you some addendums. Negative 15e. So for DC 156. Okay, so let me mark it down. Okay, DC 12586. Okay, so yes, the correct answer. So to calculate is very easy. So the total charge amount will be -50 plus 20, and then we try to distribute it to the sphere equally. So we just divide by 2, so which will be -15e, -15e. Okay, so here is another sample problem. So it says the nucleus of an iron atom has a radius about 4 times 10 to the -15 meter and contains 26 protons. Okay, what is the magnitude of the repulsive electrostatic force between two of the protons that are separated by 4 times 10 to -15 meter? So actually this sample problem is very, very easy. You just need to plug in the number in the Coulomb's law. And actually the objective of putting this sample problem is to tell you something else, something very hardcore physics. Okay, so but before going to that, let us finish this sample problem first. Okay, so here we of course need to use the Coulomb's law. Okay, so F equals K times this is an atom, which means that the nucleus, yeah, let's see, repulsive static force of the 2 proton. Here we consider the electrostatic force, the repulsive electrostatic force of the 2 proton that are separated by this distance. Because in the chemistry class, you know, we have the nucleus and then we have some electron, and then this is the nucleus. And then we know that the distance or maybe the radius of the atom, the radius of the atom is this one. So this is the radius of the atom. So, and of course there are some neutron and some are proton, but we try to estimate the repulsive force between two of the protons in the nucleus. Maybe they are distributed here and maybe here and there. They may not be accurately this radius. Maybe one is here, one is there. So the distance may be smaller, or maybe one is here, one is there. But we only try to guess a value. Okay, so yeah, so here we have a E squared because both of proton they have a positive charge of E, and then we try to calculate the distance R squared. Okay, so here 8.99 times 10 to the 9th power, and then times 1.6 10 to -19 quantity square, and then all over this radius 4 times 10 to -15 square. Okay, so this is 14 Newton, quite a large force. Okay, so this is easy. So for part B, it says, what is the magnitude of the gravitational force between those same 2 protons? So I think in physics 1, you do have already learned the gravitational force, which is F equals G times m1 m2, which means mp squared, the proton of the mass, the mass of the proton, I mean, the mass of the proton all over r squared. Okay, so here we try to consider the gravitational force because gravitational force are attractive, and the electrostatic force for the particles with the same polarity of charge is repulsive. So this is repulsive. And the gravitational force is attractive. Okay, so you don't really need to remember this one for this course because it also appears in this course only. but actually it is 6.67 times 10 to minus 11. This is the G, the gravitational constant, and then equals 1.67. Sorry, should be times 1.67 times 10 to minus 27, and then quantity square over 4 times 10 to minus 15, also quantity square. Okay, so we just plug in the number, and this number is 1.2 times 10 to minus 35 Newton, which is much, much smaller than the previous. This is the gravitational force. This is the electrostatic force, or the electromagnetic force. Okay, so this is much, so this is Fe is much, much, much larger than the gravitational force. So this is repulsive. This is attractive. So you may have questioned why the nuclear can have so many positive charge there, and then they did not break down because the electrostatic force are repulsive, and all of them are positive charge, and there are some neutron with zero charge. But at least for an iron atom, it consists of 26 of protons, 26 of this kind of positive charge. How come they can just hold together as a nuclear? Okay, so, and actually in the universe there are 4 types of forces. One is electromagnetic force, and basically in this semester you will learn about the electrostatic force, 电磁力. And another one, gravitational force. So 重力. So I think you should have learned it in physics 1 or some mechanic. So for the gravitational force. And the other two, one is called the strong force, and the other one is called the weak force, 强力或者弱力. And usually in physics class, you seldom learn about these two forces. For the weak force, it's about the nuclear reaction, like the similar like the nuclear reaction, like the fission and fusion, 核聚变核裂变. So it's called the weak force. And the strong force related to the force in between the atom, or in between the elementary particle. So in some hardcore physics, you may have known something is called the standard model of the elementary particle, 粒子的标准模型. Okay, so, and of course there are something you are familiar, like the electron, 电子, you should have known. But however, most of the other stuff you don't really know. And actually, even in chemistry class, high school chemistry class, you only know a proton, neutron, and of course electron is actually this one, you know. And so actually, if you try to separate the proton and neutron into smaller basic element particles, it can really separate into something called the up quarks and down quarks. I don't really quite remember. Maybe it's like 2 up quark and 1 down quark, and then to be the proton and whatsoever. Yes, you should try to count. For example, for the up quark, the charge is that, and then for the down quark, the charge is negative 1/3. So if you have 2 up quark and then 1 down quark, they add up to be positive 1 element of charge, positive 1e. And then if you have a 1 up quark and then 2 down quark, and then the total charge will be 0, then it forms a neutron, or something like that. And then why the atoms can have so many positive particles? It is due to the gluon. In Cantonese, it's called gaoji. So it's like the glue to glue the cross together so that it can hold up to be an atom. Okay, so it's pretty much like that. Some hardcore physics, if you have interest, you may check it on the textbook. Something like 40-something chapter 40-something has a chapter about this one. If you're interested, I think this is very hardcore, so just skip it if you don't really interested in it. Okay, and another one is called the charge is conserved. Charge is conserved means you cannot create a charge or cannot discriminate the charge. So before some action, there are total charge amount of something, and after some action, the total charge amount will remains the same. Okay, so the charge can only move from one place to another, but you cannot discriminate the electron. So if you have learned the high school chemistry, when you try to write the chemistry formula, then you have that kind of feeling. Yeah, the charge on the left side and right side should be the same. Okay, so here the two of the most possible reaction for the charge is like if you have a electron, and then this one is called a positron. The positron, 正电子. Positron, 正电子. So and then they touch each other, and then they will eliminate some gamma ray or some high energy particle without charge. So some eliminate some energy. And then another way is if you have a large amount of energy, then it can split into electron and positron. Something like the thunder ray can form the positron, but we seldomly find it elsewhere in the Earth. Okay, so we just talk about something called the gamma ray. It's a type of high energy particle. And actually, we will talk about this figure or a similar figure in chapter 32, I think, chapter 33. I think chapter 33. Okay, but simply speaking, when we talk about the high energy particle or high energy EM wave, electromagnetic wave, EM wave, 电磁波. Okay, so we need to care about one is called the wavelength, one is called the frequency, And in high school physics, you may have learned a formula like E, the energy of a particle is of a photon is like H times F. So this is the constant, and then this is the frequency. So which means that if the frequency is higher, the energy of that proton will be should be photon is higher. 光子. The photon will be higher. So here you can also check gamma ray here. Gamma ray is something like the highest energy particle. So the frequency of it is around this level, 10 to the 9th power, 10 to the 20th power, or even higher. And then lower, a slightly lower energy will be X-ray, soft X-ray, and hard X-ray. So if you need to do the body check the lung or whatever, then you will need to take the X-ray. And here is the visible light. So we have a rainbow for the visible light. And then slightly high energy will be the ultraviolet, 紫外线. And then slightly low energy will be infrared. Okay. And then for even lower, it is microwave. So it is 10 to the 9th power. So when you try to use the something called the Wi-Fi, if you use Wi-Fi, it is using 2.4 gigahertz band or 5 gigahertz band, or maybe even higher for the millimeter wave for the recent standard. But yeah, maybe for 4G, you are also using this part for the wireless communication. And even for higher, up to that part, tens of gigahertz, then the 5G, the 5th generation communication will try to use these parts. Something called a millimeter wave. Okay, around there. So yeah, and for lower frequency, like here, FM radio, if you try to listen to the Macau radio stations, it is like 100.7 megahertz for the Macau radio station. Okay, so another equation you need to care about is C equals F lambda. So this is the speed of light, which is 3 times 10 to the 8th meter per second. And then this is a frequency, this is the wavelength, which means that if you have a higher frequency, you have a shorter wavelength. If you have a lower frequency, you have a longer wavelength. So which means that this part has a higher frequency. Then the wavelength is very, very short. Then it can go through something. For example, for the X-ray, it can go through your flesh and then to see a bone like that. And for this part, it has low frequency, which means the wavelength will be high. Okay. Okay, so I think we have one or two. Yeah, we have. I think I can just skip this one, and then let me try to explain this one so that we can finish off this chapter. So let me talk about the additional example. So we have 3 identical conducting sphere initially have foreign charges. Sphere A, Q, sphere B, minus 6Q, sphere C, 0. And then sphere A and B are fixed in place with a center-to-center separation that is much larger than the sphere. So we do 2 experiments. In experiment 1, sphere C touch A first, and then they separate. And then sphere C touch B, and then it will remove. And then in experiment 2, we the same initial state, but we reverse the procedure, which means sphere C touch B first, and then separate, and then touch A, and then it separate. So it asks you what is the ratio of the electrostatic force between A and B at the end of experiment 2 to experiment 1. So let's check it one by one. So at the very beginning, A has the charge of 4Q, and then B has the charge of a negative 6Q, and then C have the charge 0. As here, A 4Q, B negative 6Q, C 0. Okay, so for experiment 1, so the first step is to touch A and B first, A and C first, like C and A first. A and C touch each other, which means that after this action, the charge on A and C will be equally distributed, which means that it should be 2Q and then 2Q. And then for B, negative 6Q remains unchanged. And then the second step is to touch C and B and C, so that A doesn't change. And then here, negative 6, and then plus 2 is negative 4. Negative 2 divided by 2 is negative 2Q, negative 2Q. Okay, so here it is the charge on particle A and B. So we need to care about these two values. And for experiment 2, at the initial state, minus 4Q, minus 6Q, 0 at the beginning, as the same as experiment 1. Here we try to touch BC first. Okay, so we try to touch BC first. So try to swap the order and then try to touch AC. So when we try to touch BC first, so negative 6Q plus 0 is negative 6Q, divided by 2 is negative 3Q. So we have negative 3Q, negative 3Q, and then 4Q here. And then the next is to touch A and C. So 4Q minus 3Q is Q, and then divided by 2 is half of Q. Q over 2, Q over 2, and then negative 3Q. So here we also want to consider these two values. So when we try to consider F2 over F1, so it should be something like K times Q over 2 times negative 3Q all over R squared, and then over K times 2Q negative 2Q, and then over R squared. Maybe you just take the value, just care about the ratio of the magnitude. Okay, so most of the value can be cancelled. So K can be cancelled, Q can be cancelled, R squared can be cancelled. So the only remaining stuff is 3 over 8. So we have negative 3 and then 2, 2, 2. So it is a 3 over 8, which is 0.675. Okay, so this is the answer to this problem. And yeah, so let's have a 10 minutes break.